In this lecture, this is the last lecture of week 12. I am going to recap what we learnt in week 12 and then do a few practice problems. Okay. So, week 12 we discussed complex analysis. Now, complex analysis is something that is extremely elegant in the sense that you can do problems that look very complicated, okay, and you can convert them to very simple problems using complex analysis, and in particular it is used in evaluating integrals. And so, complex analysis, you actually you go from the real space to the complex plane, and then you do all the analysis in the complex plane, and finally you head back to the real space. So, what all did we learn in this week? So, in the first lecture we learnt about complex variables, we learnt about functions of complex variables, and we immediately saw how the idea of branches comes in. Then we looked at complex functions, a little bit more about complex functions. We looked at differentiability, and we saw that the criteria for differentiability yields a very strong condition called the Cauchy-Riemann equations. Okay. Then we learnt about analyticity, the idea of what it means for a function to be analytic, and we learnt about contour integration, learnt about residue theorem, how you can do integration in the complex plane using residue theorem. Then in the fourth lecture I actually did applications. So, we used complex analysis to evaluate real integrals. So, in the fourth lecture we actually worked out a few problems in the fourth lecture itself. So, today I will not I will be doing some practice problems, but I will not be doing any practice problems on complex integration, because we already did that in the last lecture. Okay, but I will do a few simple problems in complex analysis. So, let us take one problem. What are the, so this problem says what are the possible values of logarithm of 1 plus 3i. Okay, so this is a very simple quantity like logarithm of 1 plus 3i. Okay. As we saw that logarithm has log in complex plane has many branches. Okay. So, when you take the logarithm of 1 plus 3i, you will end up with many different branches. Okay. And so let us try to write it out. So, what we will say is that 1 I can write as e to the 2 pi mi, okay, plus 3i I can write as 3 times e to the pi I into, now if you want I is e to the pi I or e to the 3 pi I and so on, or e to the 5 pi I and so on. So, I will write 2n plus 1 where m n goes from 0 plus minus 1 plus minus 2 and so on. Okay. And you are going to take logarithm of this. So, I mean I can do another step, and I can write this as so if m equal to n equal to 0, okay, if m equal to n equal to 0, okay, then this is just 1. So, what I am going to do is to okay, so let me do this slightly differently. So, I will say 1 plus 3i, okay, this so 1 square plus 3 square is so I will write this in polar coordinates, okay, in the following way. So, I will write it as 1 plus 9, that is square root of 10, okay, e to the I. Now, theta is tan inverse of 3. Okay. So, I will write it in this way, okay, and now I can also write this as square root of 10 e to the I tan inverse 3 plus 2 n pi. Okay. So, I can write it in this way, and now I can take the logarithm, okay, n equal to 0 plus minus 1 plus minus 2 and so on. So, now logarithm of 1 plus 3 I, okay, this is logarithm of root 10, okay, plus I times tan inverse of 3 plus 2 n pi. Okay. Okay, so, these are the possible values. So, you can put different values of n. If n equal to 0, then it will just be logarithm of root 10 plus I into tan inverse 3. If you put n equal to 1, then it will become plus I tan inverse of 3 plus 2 pi and so on. Okay. So, let me write this in a slightly different way, root 10 plus I tan inverse of 3 plus 2 pi I into n, okay. And you can put different values of n and you will get different values of logarithm of 1 plus 3 I. Okay. So, this is an example of what we learnt about different branches of a function. Okay. The function is the logarithm function, and we know that logarithm has many different branches. Okay. Now, what is important in this is to, in this case, when we had logarithm, if you just write it, if you just write 1 and 3 I, okay, then you cannot factor it, but if you write it in polar coordinates, okay. So, this is polar coordinates, okay, then the logarithm, it becomes easy to take the logarithm, okay. So, in this case it is better to work in polar coordinates. Okay. So, now the next function, okay, next problem that I want to do is to calculate the poles of z square divided by z square plus 1 cube and z plus 2 square. Okay. So, the poles are given by the denominator going to 0. Okay. So, if you take okay. So, the zeros are at z equal to 0. So, z equal to 0. So, the numerator going to 0 will give you 0 of the function. So, poles are at this point. Okay. Now, notice that I could directly write the poles at this point, because the zeros, there is only one 0, z equal to 0, okay, and z equal to 0 is not a pole. Okay. So, we do not have to worry about complications that arise because you have 0 by 0 and so on. Okay. So, if this equal to 0, so there are total of, we will see how many possibilities are there. So, z plus 2 whole square equal to 0 implies z equal to minus 2. This is a pole of order 2. Okay. So, that is one possibility. So, this is z equal to minus 2. Then you could have z square plus 1 cube equal to 0 implies z plus I, z minus I whole cube equal to 0. So, that means you have z, so I will write this as z plus I cube, z minus I cube equal to 0. So, that implies that z equal to I and z equal to minus I. So, these 2 points are poles of order 3. So, you have one pole of order 2 and you have 2 poles of order 3. Okay. So, I mean you can just if you just look at this polynomial, okay, this is a degree So you have z square and you have z square cube. Z square cube is like z raised to 6. So the leading power of the polynomial is z raised to 6 into z raised to 2, which is z raised to 8. Okay. And here you have a pole of order 2 and 2 poles of order 3. So 3 plus 3 plus 2. So total 8. The total order of the poles is 8, okay, which matches with the polynomial. Okay. So now so your function has 1 0 at z equal to 0 and it has these poles. Okay. So just to summarize, you have a 0 at z equal to 0, you have pole of order 2 at z equal to minus 2 and you have poles of order 3 at z equal to plus minus I. Okay. So these are all the poles and the zeros of this function. Okay. So once you have the poles and the zeros, then it is very easy to do the complex plane integration. Okay. Any contour integration can be easily calculated once you have the poles. Okay. So I will not be doing problems on that because we already saw that in the last class. So with this we have completed this course, advanced mathematical methods for chemistry. Okay. And through these 12 weeks I have taken you through various topics in various mathematics topics which are used quite widely in chemistry. Okay. And I will just summarize some of the topics that we did. They included vectors, vector differentiation, vector integration, matrices and lot of things with matrices. We learnt about special functions, okay, like the gamma function and so on. Then you learnt about optimization, constrained optimization. Okay. Then we learnt about ordinary differential equations. We looked at various first order and second order differential equations. Then we also looked at nonlinear differential equations where we analyzed the phase plane and did the stability analysis. We looked at integral transforms such as Fourier and Laplace transforms. We saw partial differential equations, probability and statistics, and complex analysis. So there are a whole there is a whole variety of mathematical tools that are extremely useful in all of science and engineering. Okay. And particularly I mean in chemistry we see lot of these come up and in very I mean they sometimes show up during when you are doing research or when you are learning, when you are taking advanced courses, you will often use lot of these mathematical techniques. Okay. And the idea is that as a chemist, when you see something that requires mathematics, it should not you should be perfectly comfortable identifying what is the mathematical tool you need and what are the things you need to do in order to resolve whatever you are seeing in your advanced courses. So I hope through this course I have been able to convince you that that mathematics is useful for chemistry and that there are a lot of mathematical tools that you see in your when you are doing chemistry, especially physical chemistry, and that you can actually do fairly advanced things if you know the mathematics. Okay. So so with this I will conclude and I thank you for your attention.